everyone for coming. Sange decided to actually read the proof by OpenAI on the cycle double cover conjecture, and he decided that he would present it to us because a lot of us apparently haven't read it. It seems there's a lot of interest in it, so please take it away. Thank you very much.
Yeah, thanks for coming. Yeah, I voluntarily decided to give a talk about something that I didn't do. Alright, so this is about cycle double cover conjecture. That was proved very recently, last weekend. So the conjecture, or now theorem, states that every bridgeless graph has a cycle double cover. So what is the bridgeless graph edge? Right, that when you delete it, the number of edges, number of components increases. Right? So when you delete it, it has more components than tree. And what about double cover? So a cycle double cover is a list of cycles. Right? List of cycles such that every edge is in exactly two of them. So I want to explain the proof, and my goal is to show you that how I can teach for undergraduate students. So right? If I'm teaching a graph theory course in undergraduate classes, I think I can cover this. All right. Actually, so if we only care about existence of cycle double cover, I can replace these cycles by Eulerian subgraphs. So sometimes this is more, so it's not exactly equal, but we can roughly say that a list of Eulerian subgraphs such that the same condition. Why? So what is an Eulerian subgraph? A graph is Eulerian if every vertex has even degree. And when you have an even degree everywhere, you can partition its edge set into cycles. So therefore, when you have a list of Eulerian subgraphs, you can partition this Eulerian subgraph into cycles, and then you get this list. Right? And each cycle is Eulerian. Right? So if you have this list, then this is also there, and so vice versa. Yeah.
By a list of cycles, do we need distinct cycles, or they can be the same cycle?
You can have a same cycle. Like, for instance, if graph G could be just a cycle, then you have to repeat this cycle twice.
Yeah.
Right? Right? There's no other cycle. Graph is a unique cycle. Right, that's a good question. Yes. What else should I say? Any other questions? So the thing is, if you look at the many literatures about this conjecture, many of them were major theorists, so they call a circuit for our cycle and cycle for Eulerian subgraphs. So when you read the paper, it's very confusing because when they say cycle, it's actually Eulerian subgraphs.
What about loops and parallel edges? Do you allow them?
We allow them. So these are multigraphs. We allow loops, but when you have a loop, you can repeat loop twice. Right? When you have parallel edges, there's an easy exercise to remove it.
So, I have a question. What's the motivation of this conjecture?
Oh yeah, that's a good question. Do you want to sit? Right. So there was a, so this was from 1970s, and people didn't know exact origin of the problem. So when you look at the book, or I look up the references, and early references are like by Szekeres in 1970s, and also Paul Seymour has another paper in 1970s mentioning it. And there were equivalent conjectures by some other people. Okay, let me copy from my note. Italian note. This was also in 1970s, so they have paper with it. Seymour has one paper. Szekeres conjectured it for cubic graphs. Seymour conjectured it for general graphs. And they conjectured for slightly different version where every edge is in at most two of them. But it's an exercise to prove that they are equivalent. If you prove one, you can prove the other. The motivation is this stronger conjecture. So this is a strong embedding conjecture that every two connected graph has a strong embedding. What does that mean? On the surface, so strong embedding means it's a two-cell embedding, so every face is homeomorphic to disk, and every face boundary is a cycle of the graph. So it's a two-cell embedding such that every face boundary is a cycle.
You mean two connected is a vortex connected?
Yeah, the vertex connected. Because otherwise, you have if the graph is not too connected, so maybe this, then you have a face boundary which is not a cycle of the graph G, right? So if you have a cup vertex, you might have a face boundary which is union of two cycles, right?
This is not equivalent.
Not equivalent,
Okay.
but this implies that.
Yeah, sure.
This implies that now it became, no, we don't know, this is open.
I know that there's a version of this that is equivalent. I don't remember exactly.
Yeah, when graph is cubic, then they are equivalent.
Okay.
When graph, every vertex is degree 3, then these two are equivalent.
Okay, thank you.
So the reason why this implies that is because when you have a strong embedding, then you just take the face boundaries of every face. Then every edge is used by two faces. So you have a cycle double cover.
And here the surface is oriented to the surface.
Not necessarily. So there's another conjecture that you can do it on an orientable surface. So this is a question studied by Tutte and many others, but people don't know exact origins. Many others, maybe from 40s. So this is still open. Okay. And there are lots of conjectures. If you look at the some paper, there's I saw a figure where each box represents conjectures. There's an arrow for implications. Yes, this is one of the conjectures. All right. Okay. So, any other questions?
So the cycle double cover conjecture also implies this strong embedding.
No.
Only to cubic.
Only when graph is cubic. If every vertex is degree 3, then this implies this. Because when you can build the surface, right, by rotation system. Right? So at each vertex just fix in some orientation. All right. motivations. Now, let me show you the first step, which is well known, which was well known. We want to say that minimal count example for this conjecture is cubic and 3-edge connected. So first step 1. Minimal count examples. Alright, so I want to do something. Yeah, so for instance, we may assume, okay, let's minimize number of edges. Okay, so meaning that I assume the conjecture is true for any graph with a smaller number of edges. Okay, that means, of course I can assume the graph is connected without using that, right? If the theorem is true for connected graphs, then it's true for any graph. So it's 2-edge connected. Right? 2-edge connected. Does everyone know the meaning? Yeah, so k-edge connected. Right? So whenever 2-edge connected, whenever you partition into 2 sets, there are at least 2 edges. All right. Now, if I have if I have a picture like this with exactly 2 edges, now, what can we do? I can pick one edge and contract. This is not what you expected, right? So if G has an edge cut EF of size 2, then contract E. If you contract E, I'm getting a graph like this. This edge stays, but this edge becomes one vertex. Now, this graph still is bridgeless. You cannot create new bridges by contractions. So, by an assumption, this is not a count example. So therefore, there's a cycle double cover. And any cycle using this edge has to go through this vertex. Right? So I can recover cycle double cover here. Alright? So that means whenever I have a edge cut of size 2, I can reduce the problem. So that means there's no edge cut of size 2. So G is 3-edge connected. Is it good? Yeah. So I can assume the graph is 3-edge connected. Now, what should we do if I have a vertex of degree 4? So, if degree of some vertex, so I will write dv for the degree, is at least 4. Right. Now, what we do is, there is a way of converting it into, so you can, so let me say there are, among 3 edges, I can choose 3 edges carefully, so that among them I can choose 2 of them, so that I can make a shortcut. And this graph, so one of the choices will make this still 2 edge connected. Okay, this is a lemma by, so here's a lemma stating exactly that. So if you have a 2 edge connected graph, and V has a vertex of degree at least 4, and let's say E1, E2, E3 are the edges instead with V. So if G delete E1, delete E2, delete E3 is connected, then G either G minus E1 minus E2 plus E1 E2, no, not E1 E2. What is it? Shortcut V1 V2, let's say, or G minus E2 minus E3 plus V2 V3. One of them is two edge connected.
Here all of the graphs are simple or
No. You allow parallel edges. Yeah. So far, I didn't say much about parallel edges, and this was actually a homework problem in my graph theory course. So
then if E1 and E2 are just the same edge, I mean,
oh, they are distinct edges, but you're worried about this situation, right?
And you replace it by a loop, and adding a loop. If you
Yeah, but the thing is, right?
That doesn't break anything, I think.
Yeah. Right. As long as so you if they were parallel, I'm replacing this operation. I'm replacing by loop. Yeah. Okay. All right. So I will skip the proof of this because homework problem to undergraduate students. All right. So once we assume that, then how do we? So at least I need to find the three edges whose deletion is still connected. So how do I know that I can choose three edges instead of V whose deletion is connected? So one case is when G delete V is connected. If G delete V is connected, then I can just take any edge. Then I have a spanning tree of the whole graph without using E1, E2, E3. So that's good. So that's one case when G delete V is connected. Otherwise, G delete V is disconnected, right? Now because graph is three edge connected, there are at least three edges coming out of each component. Now I can discard two edges for each component, right? So I can delete even four edges instead of V, so the graph is connected. So I can always find three edges whose deletion is connected, and then use that lemma to say that I can take a shortcut. Now, once I have this graph, then this graph is two edge connected and has less number of edges. So by the assumption, there's a cycle double cover. Now, if I have a cycle using this edge, then I will replace it with a cycle using that edge, these two edges. Now, you might worry about the situation where, what if my cycle was actually like this, right? Then that cycle become this. Yeah, but anyway, in this case, you can just split into two cycles. Or if you were thinking about Eulerian subgraph, you don't have to worry about it. Alright? So that means whenever I have a vertex of degree 4 or larger, I can reduce it. Right? So that means every vertex will have degree exactly 3. Okay? So G is cubic and 3 is connected. Right? So that's, yeah. So if we prove the cycle double cover conjecture both cubic 3 is connected graphs, then we are done. Alright, so now, any questions? This is all known previously. Alright, so now next topic is I will talk about low result flows a little bit. This was invented by Tutte long time ago. Let's say gamma is a abelian group, and then a nowhere zero gamma flow of a graph G. But it's easier to define it for directed graph, let's say. Is a function from set of edges to this group gamma, and it's a flow such that for every vertex, the sum of the flow values of outgoing edges from V is equal to sum of the flow values of incoming edges. And it's nowhere zero, so phi of E is never zero for every edge. So when you satisfy these two conditions, then we call a nowhere zero gamma flow. And in this, and for undirected graph, we say undirected graph has nowhere zero gamma flow if any of its orientation has nowhere zero gamma flow. Because when you have this at this direction, if I reverse the edge, I can just multiply -1 to phi value. I still satisfy the same thing. So that's the lower zero gamma flow. And when gamma is, now I have to choose because typically I used to use this notation because G is group, right? But later we will use F2 to the 3 because I want to see it as a vector space of the field later. So when gamma is this, then G2, what is G2? 0, 1, right? So you can think of it as a like vector 0 or 1, 1, something like this. So we are assigning value like this for every edge. Now in this case, -1 is equal to 1. So adding or subtracting doesn't matter, right? So in this case, a nowhere zero G2 3 flow is a function phi from set of edges to G2 3 such that every edge is non-zero and sum of the values is 0 for any edge instant with V. So I write delta V to denote the set of edges instant with V. So why did I mention this? There's a theorem due to Jay in 70s that every bridgeless graph has a nowhere zero G2 3 flow. So you can always assign this kind of values for every edge so that no edge got 0, 0, 0 and sum of the values at each edge is equal to 0. And I can show you the proof, except I will not prove one thing. So how do we prove it? There's a theorem due to Nash-Williams and also by Tutte about disjoint trees. So graph G, okay, G has T disjoint spanning trees. If and only if something happens. So graph is T disjoint spanning trees then no matter how I partition the vertex into many sets, so for any partition V1 up to Vm of Vg, now I'm counting number of crossing edges. How many edges do we cross? Okay, so if I have m parts, if I had one spanning tree, then there must be at least m-1 tree edges crossing, right? Then each spanning tree, so these are edge disjoint by the way, each spanning tree will have m-1 those edges crossing. So there should be at least, there are at least t times m-1 edges joining distinct parts. Okay, so that's the necessary condition, right? If you have a t disjoint spanning trees, you should have at least t times m-1 disjoint, no, edges joining distinct parts of this partition. So one direction is trivial, the other direction is non-trivial, and there are some proofs known. My favorite proof is using matroid theory, matroid union. Because spanning trees are basis of the matroid, but anyway. All right, so why is this useful? This means, here's a corollary. If G is 3-edge connected, then G has 3 spanning trees, 3 spanning trees, T1, T2, T3, such that the intersection of all of them is empty. This looks like different theorem, right? Because that's about edge disjoint spanning tree. I allow having 2 trees to have common edges, right? But why? So why is this true? How to prove? Let's start with the graph G. I will make a G prime, which is obtained by doubling every edge. So replace each edge by double parallel edges. Okay? Then G prime is 6 edge connected because every edge is doubled. Now, if G prime has 3 edge disjoint spanning trees, then each spanning tree corresponds to a spanning tree of G, but I had only 2 parallel edges, right? I cannot have 3 trees using same places, right? So no edge belongs to all 3. So that's the why. If G, so it's enough to show that G prime has 3 disjoint spanning trees. G prime has 3 edge disjoint spanning trees. Now we use Nash-Williams theorem. Suppose I have a partition into n parts, right? Now each part I will have at least 6 edges coming out, right? Because the graph is 6 edge connected. So the total number of edges, right? So what is total number of crossing edges? 6 times number of things, right? Yeah, but divide by 2, right? Because I counted one edge twice, right? So that's 3m, which is bigger than 3m minus 1, right? So therefore, we have 3 disjoint spanning trees. Okay, Is it clear? Now, this means, okay, I will not show you how to reduce the richness graph. What we need is, every 3 edge connected. Because minimum count examples are 3 edge connected anyway. So I will show you that every 3 edge connected graph has nowhere zero G2 to the 3 flow. Just by taking as follows. So for any, okay, so what is a good way? Okay, let me write a lemma. For any spanning tree T, there is an Eulerian subgraph H such that edge set of H contains every edge not in the tree. So I have a spanning tree. Okay? Now, my goal is to find the Eulerian subgraph covering every edge outside. Right? Okay, I'm going to cover every edge outside. I may cover some of the edges of the trees. My goal is to cover every edge outside. How do we do that? So we have a fundamental cycle with respect to the spanning tree. So for any fixed spanning tree plus one edge will induce a cycle, right? Now I have a list of cycles, right? How many cycles? I have a number of edges outside the spanning tree. Take a symmetric difference of all of them. Then every edge outside appears exactly once, so they survive. And when you take a symmetric difference of 2 Eulerian subgraph, you still get Eulerian subgraph. Okay? So, is it clear? Right, so that means for T1, T2, T3, I have corresponding Eulerian subgraphs, H1, H2, H3, where H1 covers outside of T1, H2 covers outside of T2, H3 covers outside of T3. Then every edge will be covered. Okay? So that means I will take phi of E is like 0 or 1, depending on whether or not it's in H1, right? This second coordinate is for H2, third coordinate is for H3, right? And then since it was Eulerian, this is flow. This is nowhere zero flow. All right, so that's the already known part. All right. Now, from here it's apart from the, yeah.
I have a question about the theorem in sandwiches. Is there anything special about the power 30? Could we use the same technique for different powers?
Yeah, but the thing is, okay, so there are theorems about G2 to the 2.
Mm-hmm.
No, that's nowhere zero 4 flow theorems. But in general, you don't have I mean, if you do have 2 disjoint spanning trees, then you have nowhere zero G2 to the 2 flows, right? Because there are, people study for different groups. People study. And Tutte has beautiful theory. So you can basically say when, for which size of group you have a flow or not. And there are lots of conjectures too. All right. So we proved that every 3 edge connected graph has nowhere zero G2 to the 3 flow, assuming Nash-Williams theorem. All right. Now, how do we find the cycle double cover? Here's an idea. Let's say Okay, so let's say G is rootless and gamma is finite some set, finite set. And suppose we have, suppose there is a PE, a subset of gamma, for every edge, E of G, whose size is 2, such that for every vertex 3, the number of edges E is instant with the V having S in PE. Okay, for every vertex and for every S in gamma, if this number is even, yeah. So suppose I can find the subset of size 2 for every edge, such that for every vertex and for every element of the gamma, the number of edges inside with V having this value is even. Okay, so for any vertex, I look at it. Here's a 2 elements. Here's another 2 elements. Here's another 2 elements. Okay, and I look at this vertex. This is a bit weird. Now, how many edges contain star? Okay, there's one. So this is not this case, but all right, right, something like this, right? So in this case, the square appears twice, star appears twice, circle appears twice, and other label appears 0 times, right? So that means then G has a cyclic double coupling. Does that make sense? And why? Because just let HI be the set of edges of the graph where I is in PE for each I in gamma, right? Then this graph is Eulerian, right? So this is the new lemma that now, how do we find such a subset? So here's a step 2. Okay, so I'm gonna take a gamma to be. Okay, this thing. But let me write it as, from now on, let me write it as this notation. Now it's a 3-dimensional binary vector space. Okay, over the binary field. All right. Now, take phi as a nowhere zero gamma flow. We know it exists, and I'm assuming the graph is already cubic 3-edge connected. So 3-edge connected graph has a nowhere zero gamma flow. Now, how do we assign PE? Right? So what I'm gonna do is gonna be, for each vertex, I will think of some value. I want to choose gamma for each vertex. Okay? Now, and then there are 3 edges. Let's say this is E1, E2, E3. What are the values that I'm interested in? Okay, so for this edge, a natural choice, one of the natural choice for two values of gamma is actually these two values. Phi E1, no, phi E2, and phi E3. For these edges, I want to consider phi of E1 and phi of E2. For this edge, phi of E1 and phi of E3. So this is what, in spirit, I want to have something like this. But there's a problem. If I have a single edge, now this edge can be seen from this vertex or this vertex. So this vertex says, if this is E1, E2, it says phi of E1 or phi of E2, right? These two sets. But here it says phi of F1 and F2. These two sets, I want them to be equal, right? So what we want is to assign values at each vertex. So the goal is find PV for every vertex of the graph G such that these two things, right, they are equal. I have to write something. Right? So how do we write? So let's say, let me say, this way. For instance, one thing interesting is that phi of E1 plus phi of E2 plus phi of E3 is 0 because of nowhere zero flow condition. So if I know phi of E1, then I can add phi of E3 to obtain value of E2. Right? So what we want is like TV plus phi of, in this picture, E1. Right? And let me use this notation. What is this? Span of this, right? Span of this is only two elements actually, because it's finite vector space. It's 0 or 1, right? So when you have a subspace, A plus W prime is just A plus V for every V in W prime. Okay, this span, this thing is actually equal to 0 or phi of E3. So I want this coset is equal to Tu plus phi of not F1 plus pi of E3 for every edge. Okay. Is it clear?
How do you choose E1 and F1? You have
Yeah.
E1, E2?
Yeah. So, right. So what else? So first, let me say why they are consistent. Instead of E1, if I choose E2, phi of E2 is actually phi of E1 plus phi of E3.
Right.
So, and this is
Yeah.
consumed by that,
Yeah.
right? So the choice of E1 doesn't matter. Choose any edge instead with E3. This set is same.
Mm-hmm.
This set is also same. Like instead of F1, if you choose F2, it's the same.
Yeah.
So the choice doesn't matter. So what I'm taking is I will take PE as T V plus pi of some edge instant with the V not in E, not E, so some other edge plus this thing. Oh, it's not the same notation. Right. This is my choice of PE. Alright? If we can find the assignment of values of at each vertex such that this is consistent everywhere.
Is PE can be taken to value 0?
Yes. Right? Sometimes you might have value 0. So if I find consistent assignment of these values, then I have this situation, right? So that we have a cycle double cover. Is it clear?
No, not really. PE is supposed to be the PE up there, right?
Yeah. So I'm
So I have two endpoints of this. Why
right.
am I
So
choosing
this set has size 2.
Yes.
So this is coset notation. So this is nothing but 2 elements: tv plus pi e prime and t, because this has only 2 elements, 0
Yeah,
or this,
0 and 1.
and tv plus pi e prime plus pi e.
Makes sense.
Yeah.
How are we choosing U or V?
Oh,
Does it no matter?
yeah. The thing is, our goal is, even if you whatever you choose, whether you choose v or u,
This
Yeah.
should be the same.
it
Okay.
should be same.
Okay.
So if you have assignment of t, these t values, so that whichever direction you see, you
Yeah.
have the same value, then we have such an assignment of PE, that will implies that graph has cycle double cover.
Yes.
Yes.
Okay? So the remaining goal is to prove that such choice exists. Alright? Now we need to recall some linear algebra. When you have a matrix A, then you can think of the column space. C of A is set of vectors so that AX is column space. Right? So which is the span of the columns. And let's think of the kernel of A transpose, sometimes called the null space, is the set of vectors where A transpose X is 0. Right. Now, I don't know whether you remember, dimension, these two are actually orthogonal. Orthogonal complement. Right. So it's this. This is does that make sense? No? Right. Yeah. So what does that mean? So I'm collecting set of vectors, right? Let me write y here. Right? So that A transpose times y is 0. So that means y transpose A is 0. Now, and if I have any linear combination of columns, you say, what is it? So the column space is actually, so AX is a vector in a column space. Right? When you multiply X to A, then you get linear combination of column vectors. Right? When you multiply X to A, right? You multiply X, so you are making linear combination of columns. So that means if I look at the Y transpose A Z, no, Y transpose times Z. So this is inner product between Y and Z, right? What is this? Y, Z is AX, so Y transpose AX. But Y transpose A was 0, this is 0, right? So that means any vector y here is orthogonal to a vector in the column space. Now, So this means kernel of A transpose is orthogonal to every. So when I write this is a set of all vectors orthogonal to this. And now the dimension argument. The dimension of this is what? Number of something minus rank, and blah blah blah, right? All right. So this is one only lemma that we need for linear algebra. So here's a lemma for our setting. Let's say I don't need any general, I can just prove it for any vector space. So this is, let's say, f to the something, f to the n. And let's say for every edge E, I have a PE in W. And I want this to be non-zero. And let's say DE is some vector in W. Now, the following are equivalent. So one is I have vectors. There are TV in W for each V, each vertex, such that TV plus TU is in DE plus span of PE for every edge. Okay, so this is one consequence we want to prove. That's a good assignment. What is the other situation? Okay, space here. So second is for every family HE of vectors in W, so each HE is an element of W or vector in W. If HE that, so the inner product, is 0 for every HE, and sum of the HE at each vertex is 0 for every vertex V, then product of sum of the inner product of HE DE is 0. So this is second. So I want to, okay, so we want to prove that 1 and 2 are equivalent. All right, okay. So why? So let me first show you the easy direction. Suppose 1 is true. Is it clear what?
I can't find what DE was.
Oh yeah, I didn't define it yet. Eventually DE will be sum of these two values.
Okay.
And I move this to the left hand side. So TV plus TU is equal to sum of these two plus something. Okay, why does 1 implies? Suppose HE satisfy all these conditions. suppose HE satisfies these two conditions, right? Now, HE.DE, what is this value? Now, DE is, so I can write it as TV plus TU. Why? Why? Because this is equal to D plus this in this coset, right? So TV plus TU is equal to DE plus some constant times PE. But when I take inner product, PE dot HE is 0, right? They are orthogonal, so they disappear. So this is the what's left, and I'm summing it over every edge. So that means for every vertex, it's counted 3 times, right? 3 times. No, I didn't say it's cubic, but anyway. For every edge, instant would be right? I just rearranged,
Yeah.
counting same thing twice. But TV is common. So I can add this thing together, but this is 0. So this implies it's 0. So this is easy directions. What about 2 implies 1? Right? So whenever I have such a family, I want to have these conditions. So I want to make it as a problem like this. So I want to construct something like this form, AX is equal to B. And then say this has a solution if and only if. So this is solution means B is in the column space. So this is solution if and only if the null space is orthogonal to B. Right? Has a solution if and only if null space is orthogonal to B. Because of this. These two are equal. So any vector orthogonal to all the vectors in column, the null space is going to be in the column space. Okay? So that means B is contained in it. So how do we build such a thing? All right. Sorry, it's taking a little bit more time. But right, so for PE, yes, I need what is our statement? This is what we're proving, right? So let me think of the orthogonal complement of PE. This is dimension n-1. Because I start with the dimension n space, take a complement with a one non-zero vector. So that means I have a basis. There's a basis, let's say RE1, RE2, REn-1 is a basis of this orthogonal complement of PE. Now, let me take this matrix where each row is RE1. This is 1, 2, etc. Like transpose. Okay, so this is n-1 by n matrix consisting of the basis of the orthogonal complement. Now, what is this condition? So TU plus TV is in DE plus PE is equivalent to say that RE, when you multiply RE, then you are restricting to, yes, so you're restricting to this TRE, E dot DE for every edge. Am I doing it right? Something strange? I just want to restrict to the orthogonal complement because I don't care about this part. So now, what is the whole picture? I have some big block matrix A, right? So A is a matrix, huge matrix. So the rows are indexed by every edge. So every edge, we have n minus 1 rows for each edge. And for each vertex, I have T1, T2, Tn. Okay, so these are vertices, V1, V2. Right? And, right. But actually, these are also vectors, right? N-dimensional vector space. So the number column is n times number of vertices, right? And then some blocks I have maybe RE, right? And I multiply this, and I want to have a RE something here, right? So B is like RE dot RE times DE. So this is the matrix form of the same thing. Now we want to know whether this is orthogonal to the null space. So let's suppose Y is in the corners of A transpose. Right? So meaning, what is it? Yeah. So that means I'm taking linear combination of the rows. No, right, yes, right. So I have now let's say that HE to be RE transpose times Y, E. Because I had this kind of vector. This is Y transpose. For every edge I have n minus 1 values, which says how I do the linear combination of those guys. So they span exactly the null space. All right. Now, what do we know? Okay, so this means that HE is orthogonal to PE because H is a linear combination of row vectors. Row vectors are the basis of this. Okay, so that's orthogonal. And for every vertex, if I look at the sum of the HE for edges instant with V, then what do we get? Maybe I was too fast. at this moment. So this becomes 0. Why? So when I take this block, okay. So where is the vertex V? Look at the so vertex V corresponds to somewhere here, right? Now it was the null space, right? So this product with this is 0, right? This times that is 0. So therefore, this times that is 0. But you will see all the edges instead with V, right? So that's how you. So you got RE transpose times YE, right? For every edge instead with V. Otherwise, this entry was 0, right? All right. So we have this situation. So now, what was our condition? We are given the condition that whenever we have such vectors, this is 0. That was what we are given. So we have such vectors. So therefore, by the given assumption, so HE.DE is 0 for every, when I sum it over edges, right? Now let's look at the Y transpose times B. Right? What is Y transpose times B? This is for every edge. I'm summing Y transpose RE times DE, because B is RE times DE. But this was HE dot DE. So this is 0, right? So that means Y and B are orthogonal. So any vector in the null space is orthogonal to my given vector. So therefore, this vector belongs to the column space, because set of vectors orthogonal to every vector in the columns in the null space is exactly the column space. All right. So now, are you okay? We proved some linear algebra. Now we just need to complete the proof. We just have to apply this theorem, right? So what is DE? Our DE is going to be pi of E1 plus pi of E2. Oh, E1 and F1. Right? For E instant with the E1 and E2. Right? This,
F1.
oh, F1. Yes. Now, right, this is what we wanna prove. So we apply this. So take W to be gamma, right? Now suppose HE times PE is 0 and sum of the HE is 0 for every vertex. Now there's a really strange phenomenon happening. So the magic part of the proof is coming. So far everything was like routine or something you can do. So what is the magic part? All right, so let's see V, E1, E2, E3, okay?
Sorry, what is HE in the proof?
Oh,
What is HE?
oh no, this H is any HE. So I need to prove that for any family HE of vectors, if you satisfy this, I need to prove this.
Oh, okay.
Yeah. So just take any for some HE, where HE belongs to double gamma, right? Now I need to prove that the last thing, sum of the HE dot B is 0. Okay? Alright. Now, how do we prove that? So we know that phi E1 plus phi E2 that plus phi of E3 is 0, right? This was the condition by Noether flows. And now I know that, okay, so HE1 that phi of E1, no, not E1. I know that, no, PE. Remember PE is what?
Phi is combination
Hmm?
of phi e.
Pi E. Right? Okay, so I know that this is 0, right? This is given. HE2 where pi E2 is 0, and HE3 and pi E3 is 0. And now if I take inner product with H1 to here, then I know that this dot H1, HE1 is 0. So HE2 dot pi E2 plus HE1 dot pi E3 is 0. This means that these two values are equal. HE1 dot pi E2 is equal to HE1 dot pi E3, right? And if I apply E2, then HE2 dot pi E1 is equal to HE2 dot pi E3. And if I apply E3, HE3 dot pi E1 plus HE is equal to HE3 dot pi E2, right? And what else do I know? Oh, I also know that HE1 plus HE2 plus HE3 is 0. Okay, this condition. So I can basically, okay, let's say E3, if I put E1 plus E2, then I get, if I replace this by HE1 plus E2, then E1 is 0, right? Okay, so HE2 dot E1 is equal plus HE, yeah, that's it, right? That's equal to HE1 dot pi E2. And you will see that all of these values will be all equal by the same logic. So let me put this as a constant lambda. Okay? The lambda has only two values, it's 0 or 1. Right? So if lambda is 1, what happened? If lambda is 1, you can look at the HE1 dot pi E1, no, pi E2. Okay, so in this case, HE1, HE2, HE3 are all non-zero. Because if it was zero vector, then inner product would never be non-zero. If lambda is 0, then what's happening? If lambda is 0, then HE1 is orthogonal to pi. This is orthogonal to pi E2, and it's orthogonal to pi E3. But pi E2 and pi E3 are spanning. They are linearly independent. So that means HE1 is in the span of pi E2 and pi E3 complement. It's orthogonal to both vectors, but this complement is one dimension. Right? This was two dimension. I take a complement inside the three-dimensional vector space. So this is one dimension.
Why is the phi 2, phi 3 linearly independent?
So the thing is, if they are dependent, so I know that both are non-zero.
Oh, right.
Both are non-zero, and their sum is non-zero. So, and actually, this is equal to pi E1, pi E2, the span of this all three things. Because one of them is sum of the two others. So this is dimension 2. So that means all these vectors belong to this linear one-dimensional vector space. But in this vector space, one-dimensional vector space only has two vectors, 0 or non-zero. Right? And then when you add these things together, this has to be 0. So that means even number of them is 0. No, even number of them is non-zero. Right? So, okay, now what's left? So lambda is equal to the number of non-zero entries. Non-zero HE1, HE2, HE3, modulo 2. If it's 1, everything was non-zero. So odd number of them were non-zero. If it's 0, even number of them are non-zero. Alright, so this is strange. And this is the key observation. Now, let's look at the final line. So what that means is, if I add this thing over every vertex, this is exactly number of non-zero HE, right, at some vertex. Yeah, am I? All right. All right, so let me look at the HE.DE. Our goal is to prove this, right? But DE had two values. One from one end, the other from the other end. So for every vertex, so I can rearrange this. Is it clear? So this is HE dot, let me write just phi of E1 plus phi of F1, right? But this is for every edge. But if I do it for every vertex and just take a corresponding thing, then for every vertex and for every edge instantly, it's gonna be HE dot phi of something. Am I doing all right? Oh yeah, phi of E. This is E is different from this E, right? E prime. Right? E prime is instant with E at 3. Now, this sum is now equal to the number of non-zero entries. So number of non-zero HEs at 3. And I'm adding for every vertex. Okay? But every edge is counted twice. One at one end, the other at the other end. So this number is counted twice. So therefore, total sum is 0. Modulo 2. That's the proof. Sorry to take longer than I spent too much time at the beginning.
Then let's thank our speaker. Any questions?
Can I ask one quick question?
Yeah.
So it seems that this proof years that for every Bluetooth graph
Every-
every Bluetooth graph and
uh-huh.
Bluetooth graph contains distinct almost 8 Eulerian
Yes.
graphs that covers the getting a double covering the G. So do you think this the number 8 is optimal or
No.
Okay,
No.
We know it's not, right?
so my question is this number 8 is
So actually, people say K cycle double cover. If there exists K Eulerian subgraphs doing the same thing. So this proof says that we have 8 cycle double cover.
Yeah, we'll just do 6 with Fossimus.
No.
You get 6.
No. So it's open.
Ah.
Open for other values. Because if you prove for any K, then you prove the cycle double cover conjecture.
Yeah.
Right? So cycle double cover conjecture was open, right?
No, that's not what I'm...
Yeah. So no matter 6 flow doesn't give you this kind of Eulerian subgraphs. And the conjecture is that there is a 5, so this is conjecture, there's a 5 cycle double cover.
Is this related to the nowhere 0 5 flow conjecture or?
Yes.
Okay.
So there's a stronger conjecture, there's an orientable 5 cycle double cover. Then it implies no zero 5 conjecture. So the orientable cycle double cover is that you orient the Eulerian subgraph in such a way that every vertex has same number of incoming and outgoing edges. And then when I look at an edge, I have a one Eulerian subgraph going this way, the other Eulerian subgraph going the backward. So if I have a orientable 5 cycle double cover, then I can not only prove the existence of 5 cycle double cover, but also I can use that to prove the Tutte's 5 flow, no zero 5 flow conjecture. So it's stronger.
Other questions?
Two questions by Kim Ji-won.
Questions from Google?
Yeah, YouTube. So does the proof have matured analogy?
Matured. I don't know.
Second one is, can we find a recycled double cover by varying the nowhere zero Z2 to 3 flows and using this proof?
Hmm?
So can we find all the cycle double covers by varying the nowhere zero flows?
Oh, you meant the question is like, is every cycle double cover coming from some nowhere zero flow? So given a cycle double cover, can you construct nowhere zero flow? Nowhere zero. With some bad values, it's possible. Yeah. If I can cover graph by K Eulerian graph, then I have a G to the. If I can cover by K Eulerian subgraph, then I have a nowhere zero G2 to the K flow. So you have approximate boson, but not interesting.
it seems that it's just a linear algebra. So is there exist a polynomial algorithm to find the cycle double cover?
Yeah, but the linear algebra is polynomial time solvable, right?
Yeah.
So
But the flow
Huh?
depends on the flow. Could you
oh,
find-
exists the flow. The Nash-Williams algorithm. So finding 3D spanning tree can be done efficiently. This is Matroid
Oh.
algorithm, Matroid union theorem. They have efficient algorithm, so you can find the noise of A flow, I mean G2 to the 3 flow, and then from there I can find this initial flow and then just plug in the linear algebra computation, so it can be found efficiently. Yeah.
All right, then let's.
Oh.
take
Oh,
a-
cat.
Sorry.
Had people tried to use the nowhere zero flows before? Like, I guess I'm curious what was so innovative about this
Using noise flow.
to try and prove the cycle double
Oh yeah,
cover?
I mean, similar set of people try both. So there are a lot of theorems connecting these two.
Mhm.
So CQ Zhang has a book
Mhm.
in our library titled Noise Flows and Circuit Cover.
Mhm.
And he has also one book only about cycle double cover conjecture. So it's at the end of the bookshelf. So,
But now, let's thank him again.
thank you.